Hi friends, welcome to this class. So we were discussing about the stereochemistry other than carbon, right? So in this video we are going to discuss the stereochemistry of silicon compounds, right? So silicon belongs to carbon family. So if you write the carbon family, carbon, silicon, germanium, tin and lead. So it is the carbon family we can see. So in carbon we have seen that if a carbon attached to different atoms A, B, C and D, let me not call it as C, it is E. So if a carbon attached to different atom A, B, E and D, so this carbon we call it as asymmetric or chiral carbon, and these carbons are optically active, right? So these carbons will be optically active, so they have the ability to rotate the plane polarized right towards right or towards left. It rotates towards right, then we call it a dextrorotatory. If it turns toward left, then it is called leo rotatory, right? So these things we have studied, right? Similarly, since silicon germanium belongs to same carbon family, so same with silicon also, if we have different atoms attached to silicon, right? So it is A, B, C, D, then these compounds will be optically active. And I have told if same two atoms are attached on carbon or silicon, that will be optically inactive because they will be having plane of symmetry, right? So because whenever the symmetry elements are there, the molecule itself becomes optically inactive inactive. But these when attached to different, both these don't have any symmetry elements, no symmetry elements, no symmetry elements, so these will be optically active. All right, so let us see few of the compounds which the scientists discovered in silicon. So the scientists, they resolved few compounds which were optically active. They resolved some compounds which are optically active. For example, the three compounds I'm going to write which the scientists resolved them: ethyl, propyl, this is CH2 benzene ring, right? Benzyl, right? And it is here SO3H group is there, right? So see, all these atoms attached are different: propyl, ethyl, benzyl, and this is parasulfoxide benzyl, right? So since all these atoms attached to silicon are different, so this compound is optically active and the scientists resolved it. Similarly, they have given two more compounds, that is silicon attached to ethyl, here it is methyl, here it is benzene, that is phenyl, and here we have substituted benzene, benzoic acid, right? So this is the thing. So here also four atoms are different: A, B, C and D. All four atoms are different, so such silicon is asymmetric. Silicon is also asymmetric. The whole molecule, if you see, it is asymmetric. You should understand, asymmetric means the whole molecule is asymmetric, means no symmetry elements, no symmetry elements. Symmetry elements means symmetry elements consist of plane of symmetry, center of symmetry, axis of symmetry and mirror plane symmetry. So these symmetry elements will be absent in such molecule. So such molecules we call it as asymmetric molecule. So this molecule will be optically active. So this is also optically active. So this molecule is also resolved by the scientist, right? So these two molecule. One more molecule, let me give you. So we have this one, silicon attached to methyl phenyl. Here we have halogen, chlorine, bromine, iodine, any of the thing. So general have written X, and here we have naphthalene, right? Naphthyl we call. Sometimes they will write the structure like this. Otherwise, sometimes they will directly write NP, right? So naphthyl, you should understand if they are right. So this compound is also optically active as it is attached to four different atoms: 1, 2, 3 and 4. All atoms are different, so it is optically active as a symmetric molecule it is, right? So once you understand all these things, Let me give few reactions of this silicon, right? So now I have taken this compound. Here NP means naphthyl, same as above, right? So naphthyl, so you can write by structure by yourself. Here I have chlorine, right? Here I have above the plane methyl I have, and below the plane I have phenyl, right? To this if I add methanol, MEOH, so if you see this silicon is there, right? It belongs to carbon family. After carbon, next we get silicon. But carbon, it is having 2s 2p, whereas for silicon it is 3s 3p and 3d. So it will be having empty 3d orbital. So empty it is. So silicon will be having empty 3d orbital. So this silicon can occupy this lone pair like this. And this chlorine is a living group. So first what happens, this silicon in 3d orbital, this methanol OMe will come, this H plus will go as H plus only, right? And here chlorine will be there, and here naphthyl is there, and here we have methyl, and we have phenyl. Like this the reaction happens. Later on what happens, this chlorine is a good living group. So this bond is found because this silicon has empty 3d orbital. Later, this chlorine will leave the system as it is good living group. So it will live with electron density because the silicon has got electron density. That electron density will be present in 3D, empty 3D orbital, right? So this is 3D orbital, this is empty. So this methanol lone pair will be occupied in 3D orbital. Later on what happens, this chlorine will take these two electrons and live as Cl minus. So Cl minus H plus they will combine as HCl. So we will get this product. So we will get silicon. Now we got naphthyl will be there as it is, methyl will be there as it is, phenyl will be there, but we got OMe instead of chlorine. So if you see, yes, if you see, initially this compound is there, right? This compound, it is optically active because all atoms attached are different, but it used to rotate the plane polar right towards dextrorotatory, so plus. But later, after this methanol when reacted with this, we got this compound right side which I am doing circle, and they checked the stereochemistry of it. It rotated the plane polar light towards left, so Leo rotatory minus sign they showed. So from plus to minus it is converting. So that is nothing but inversion. Right here, inversion in stereochemistry is happening. So from plus to minus. So here I had A, B, C, and chlorine was there. When I added methanol, so this lone pair attacked here, chlorine, this is silicon, left the system. So this is nothing but SN2 on silicon. It is like SN2 through a transition state in which chlorine and OMe will be opposite, and other things will be there, A, B, C. So this will be the transition state which we will study in SN2 reaction. Later on chlorine leaves the system with electron density, and we will get this product A, B, C, and OMe. So if you see here, it was plus, now it has converted to minus, so inversion. So whenever you say SN2 reaction on silicon, there will be inversion in stereochemistry, right? So these things you should remember, right? Even in SN2 you have studied inversion in stereochemistry, SN2. Yes, N2 we will write like this. So inversion stereochemistry, same thing you have observed. So these reactions they will ask in exams. So you need to remember these things, right? So once you understand these things, let us next let us move on with the next example. So here what I did was I took the same naphthyl, phenyl, methyl, but here instead of taking chlorine I took hydrogen. To this I added BeCl3, trichlorobromine, right? There when I did, it also found one transition state like this. Other things remains as it is, phenyl, other thing remained as it is only methyl. But the thing is, this silicon hydrogen bond was weakened like this, and this hydrogen was bonded to this boron. Boron was having 3 chlorine, right? 2 chlorine will be there, and other chlorine was weakly bonded to this silicon as I have shown it. So it formed this square like transition state in which this hydrogen later on replaced by this chlorine. So this hydrogen was taken from by bromine, and this chlorine was taken by silicon, and we got this product silicon naphthyl, right? Other thing remained as it is, phenyl will remain as it is, methyl will remain as it is. Instead of hydrogen, here we got chlorine, right? So if you see, because of this transition state, they named this transition state as a four center metanion. They named this because of this transition state. There was retention in configuration. They observed that initially it was plus. After this transition state, this hydrogen was replaced by chlorine, but the configuration was R. R means, sorry, plus. So initially it was plus. After reaction, it was plus. Reacted with BlCl3. Only thing is here hydrogen was replaced by chlorine, but plus plus. So it is retention. In above case, what happened? Initially it was plus, right? So initially it was plus, reacted with methanol, it formed minus, right? What happened here? Chlorine was there, sorry. So this is the problem. Sometimes it happens. So initially chlorine was there. That chlorine was replaced by O-methyl, OMe. So here inversion is configuration. So this is nothing but inversion, right? So this is the thing. So I hope you know now what is retention, what is inversion. Retention means configuration remains the same. Inversion means configuration changes, opposite. So retention of configuration we call, and inversion of configuration we call, right? So this is about the reactions, right? Once we studied these reactions, let us see one more reaction, that is C. So these are the things, right? Retention in configuration, right? So this is about silicon. Next, carbon, silicon. Next comes germanium, right? Let us see the stereochemistry. This is the important reaction they will ask. So similarly, like silicon, as I have written for 3 compounds above, this germanium compounds will also be optically active. Optically active when this germanium is attached to 4 different atoms like A, B, C, and D. Those compounds will be optically active, and these compounds are resolved also. Scientists, they resolved these compounds and they saw these compounds were optically active. They rotated the plane polarized light, right? So as same of silicon, right? So let us see few reactions of this germanium. So they had this compound, this germanium attached to 1 hydrogen and 3 R group. So directly I will write R3, means germanium attached to 3 R and 1 hydrogen. And they saw that its stereochemistry, they saw it was negative. Minus means it rotated the plane polarized right towards left side, right? When this germanium compound, they added to this chlorine, Cl2 chlorine, they saw that this hydrogen was replaced by chlorine, and they got this product R3 germanium, and here we had chlorine, right? So this was the reaction. But they saw that here it was plus, right? Here it was plus, now it became, sorry, here it was negative, now it became positive. It means here inversion is happening, right? So this reaction you need to remember, right? So in book also they have given only like this, no much explanation, so I am just writing. Further, when this the same compound they added with LiAlH4, so H4 means they will be rich in hydride, so this chlorine will be replaced by hydride, right? So it was plus, and they got one more product. The product was this thing. Here R3 will remain as it is, germanium, and chlorine is again replaced by hydrogen here, but it was plus right here. It was plus, and here it was plus. So here retention happened, right? So how retention happened, why inversion happened, it is not explained in book also. Just you need to remember. So initially hydrogen was replaced by chlorine, and if you saw the stereochemistry from minus to plus it was, so we call it as inversion. Later when we added LiLH4, this chlorine was replaced by this hydrogen, but if you see check the configuration, plus remained plus, so it was retention, right? So these things they observed. Later the same compound Re3 germanium hydrogen, right? To this compound when they added N-butyl lithium, N-butyl lithium, so N-butyl will be having minus plus here. So this proton it will take, right, as H plus, and this lithium will combine with this germanium, and we got this product. Other things remains as it is, R3 Ge, here we will get Li. So lithium minus Li plus. This bond will be more ionic compared to covalent. If you see ionic character, it will be around 60% ionic, and 40% will be covalent, right? So this bond will be more of ionic, right? So when they got this compound, when the same compound when treated with n-butyl lithium, they got this product, right? Later on, what they did, they added to this compound, they added carbon dioxide, CO2. They found out that it formed this product, that is R3 germanium COOH, right? It formed this product, and its configuration is plus here, right? It formed this product. Further, what they did, they added one more reagent, that is CH2N2, CH2N2, and they saw that they got this product. Here acid was there. When they reacted with this diazomethane, they got R3Ze. Acid was converted to ester, CH3, and configuration they saw, it was plus, and here also it is plus. So it was a retention, right? So these reactions you should remember, they will ask in exam. So how this reaction happened, I can tell you that. So the thing is, whenever we have acid RCOOH, so acid means it has the ability to give H plus. So I can write like this, RCOO minus and H plus, and this minus is there, right? That will be stabilized by resonance like this, right? No doubt. So this is what we will get. And this CH2N2, this structure, you know what it is, CH2N2, CH2N2, it will be like CH2 minus N triple bond N plus. So minus plus on same molecule, so we will write neutral like CH2N2, but it will be like this, right? So this negative charge is there on CH2, so it has ability to take this proton, so it will take. So what it will form, CH3, now it became neutral, and N triple bond N plus it is, right? Later on, what happens, this nitrogen N2 plus, this N triple bond N plus is nothing but N2 plus. It is a world best good living group because it has got positive charge, but if it gets its electron density like this, it will get its lone pair back. So what it will happen is that this negative charge is there, right? So that will attack this CH3, and this will take its electron density and moves as N2, N2 gas, N triple bond N, both will be having lone pair, so it become neutral. So it will go out as N2 gas. So what happened? We got this RCO, O was there, and it is attached to this CH3. So we got this product. So what is this? This is nothing but ester, which we got above. So from acid we got ester. So see, this was acid, we got this ester. So with retention of configuration, right? So this reaction which I have written here, you should remember, right? So this is the reaction. All these reactions you should remember, right? They will ask in exams. So this is the stereochemistry of germanium and silicon. In this video, let us keep it for this only, just to check these reactions. Sorry, yeah, just you check these reactions. These reactions you have to remember these two reactions, right? Where retention happened, why inversion, right? So these things once you remember, then it is fine, right? So in next class, let us discuss few more concept of this stereochemistry other than carbon. Till then, take care and have a great day.